All right, hello class. So welcome to this video. We're going to go over the homework problems for the 1.3 lesson on dot plots. So looking at this first problem here, it says we have some data on the lengths of the first 25 words on a randomly selected page from Harry Potter and the Prisoner of Azkaban. So given this data, first they want us to make a dot plot. So let's go ahead and based on the data that we have here, we have pretty small numbers. So we can, on a number line, we could start at 0 and count all the way to, say, 12 or 13, or maybe even stop at 11. But I'll go a little bit past 11 and I'll go to 12. So let's do 0 all the way to 12. And we can go by ones or by twos. Let's go by ones here. And so we're going to label the x-axis. The x-axis is, in this case, the length of the words. All right, so then we're going to go ahead and stack dots here until we finish all of the data points. So for 2, we have should have 1, 2, 3, 4, 5, 6 twos here. Oops, so you want to do it at the 2. So 6 twos, I don't think there's any more. There's 4 threes. Looks like there should be about 6 fours. 1, 2, 3, 4, 5, 6. We have 2 fives. 1, 2. We have 1 6. We have 2 sevens. 2 8s. We have 1 10. 1 11. All right, and there's our dot plot for the data. So now we're going to explain what the dot above the 6 represents. So there's only one dot with that represents the 6. And remember, this is the length of the words in The Prisoner of Azkaban, right? So in a randomly selected page from Harry Potter and the Prisoner of Azkaban. So this is just saying that, if you randomly select a page, then that page is, let's see here. This is the number, yeah. So explain what the dot above. So if you look at it here, it says here are data on the lengths of the first 25 words. So they randomly select the page and they pick the first 25 words on that page, right? So each of these dots represents, the words on that page. So if you look at 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you look at number 6 and you look at it in the data here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, right? So this right here. So we look at all the words, and well, the 16th word happens to have 6 letters. Okay, so it happens to have a 6 letters. So the length of the 16th word is 6. And so that's really what this represents here, is that the 16th word in a randomly selected page has 6 letters. Okay, so that's really what we want to look at here. So in a randomly selected page, right? The 16th word from the book, and I won't title the book, I'll just say, from the book, has 6 letters. Okay, so So basically that's what the 6 represents, 6 letters, but the dot is just a 16th word in that book. So that's really all they're looking for, just to kind of interpret that. So now they're asking what percent of the words have more than 4 letters. So you're going to look at the dots that are 5 or greater. So it looks like these dots here. So in that case, you have 2, 4, 6, 8, looks like 9. So we got 9 out of, and then we have a total of 25 words that we chose. And so we got 9 over 25. And then of course we got to times it by 100. And we'll get that as a percent. So it looks like 36% there. So we're going to times it by 100. And that's 36%. All right. And that's what they're looking for number 1. All right. So number 3, we're looking at the EPA estimates for gas mileage for 21 model year 2014 cars. And so they just want us to make a dot plot of the data. So that's simply what we're going to do. So for this data has larger numbers here, right? So what we're going to do is we're going to start, we're going to have to choose a scale here. So since we have, 20s, we have 50, we have one that's 51. So we have pretty large numbers. So let's go ahead and go by 5s here. And you can start at 10 and go by 5s, because our smallest number here is, if you look at the smallest number, let's see here, it's about 8, it's 18. So 18 is the smallest. And looks like 51 is the largest. So yeah, let's go by 5s, I guess, and go from there. So we have 0, 5. And 55. Okay, so we'll do that. And you don't have to go by 5s. It's just a scale that I chose. So in this case, if we look at the numbers, we have 1, 2, 3, 4 18s. So we're gonna go ahead and stack that. So 4 18s, that 18s around here, so it's like half. So let's do that. 1, 2, 3, and 4. Then it looks like we have, for my next number, we have 19 and 19. So it looks like we have 2 19s. Now we're looking at 20. We have 1. We have 220. It looks like 120, 2 20s. Looks like we have a bunch of 21s. So 1, 2, 3, 4, 5 21s. We have some 22s. We have 1, 2 22s. We don't have any 23s from what I can see, but we have 24. So 1 24 and 2 24s. Then we don't have any 25s. So it looks like we're going straight to 28. Let's see here, 28. So that's going to be around here. We have one of those. Actually, looks like 2 of them right here. And then looks like we have a 51 for the final. Okay, so 51, let's do that over here. All right, so we got our dot plot, and that's really what they're looking for. They're not asking us to do anything else. But if they were asking us about the shape, then we would say that this, if you look at the shape here, well, it kind of looks skewed to the right. but that's not really what they're asking for. They're just asking to do the dot plot. All right, so for number 9, we have the dot plot shows the results of rolling a pair of six-sided dice, finding the sum of the up faces 100 times. Describe the shape of the distribution. And so all you're doing is describing the shape. So you can say skew left, skew right, or symmetric, or roughly symmetric. So if you look at the shape, it looks roughly symmetric. So it looks roughly like a normal distribution. So we're gonna say it's approximately symmetric or roughly symmetric. So approximately symmetric slash, and then we can also call it approximately normal because it looks like a bell curve, right? If it looks bell shaped, then we call that a normal distribution. So approximately normal. Okay, and that's it. That's all they were looking for that one. Number 12, the last one. The following parallel dot plots display the lengths of the best 15 movies in each of 3 decades, according to the IMD, the Internet Movie Database. Compare the distributions of movie lengths for these 3 time periods. So what we're gonna do. So this is so we have this is a parallel dot plot. So we're gonna actually compare these 3 time periods for movie lengths. So we're going to talk about their spread, and then we're going to talk about their center, approximately. And so if you look at the bottom one, the more recent movie decade, right, 2000 to 2009, it looks like it has. Let's see, the movie length. It looks like if you look at the center. So I'm going to kind of draw roughly the center, right? The center is roughly around here, or so. And then if you look at if you were to draw this one, the center is roughly around here. And then for this other one, well, you have something that looks like that, right? And the center is roughly around here. So it looks like the one that has the highest center, right, is the recent decade. Okay, so on average, it looks like the movie length is highest for the recent decade. Okay, so it looks like we're going to say the average movie length is highest in the recent decade. Okay, in the most recent decade of the 3 decades that we're looking at. And it seems to be lowest in the oldest decade here from 1960 to 1969. Okay, so the lowest average movie length occurs in the 1960 to 1969 decade. So that's talking a little bit about the averages, right? And then the middle one is middle of the road as far as the average, if you were to compare them. And then for the variability, when you're comparing distributions, you want to talk about their center, you want to talk about their spread, and then maybe gaps in the data or things like that, that kind of stuff. So, and it looks like if you look at the shape here, the shape for the top one, it looks skewed to the right if you look at it. This one also looks skewed right. And the bottom one looks approximately normal. So I'm gonna go ahead and go on a limb and just say it's approximately normal, approximately symmetric. It's not exactly symmetric, but it's approximately so, especially more so than the other distributions. But if we look at the spread is roughly the same. I would say roughly the same because they're all, around this area as far as movie length, right? In the left side. And on the right side, they're all approximately there. So the variability is about the same. The spread is about the same. Okay, so the variability, v lengths, is similar across all 3 decades. Okay, so that's a little bit about comparing the distributions, and that's it for the homework assignment. Very simple. It's just interpreting the dot plots and making some dot plots, and I'll see you guys in the next one.